Hello everyone, this is Doug here, and I'm going to talk to you about the Baeyer Villiger reaction right now, which is another type of oxidation that you'll see with carbonyl compounds. So the Baeyer Villiger oxidation, it's just a reaction of aldehydes and ketones with some sort of peroxy acid. So we all know what aldehydes are, we all know what ketones are, and peroxy acids we've actually seen before, right? So we're talking about a carboxylic acid, so C-O-H, but since it's per, that means there's an extra oxygen in there. So we're talking about you need to add some sort of peroxy acid. This is just like what we saw for making epoxides from alkenes. We added some sort of peroxy acid. So what you're going to see is you're either going to see some sort of generic peroxy acid, which would be drawn as just RCO3H, right, because we have 3 oxygens there. Or you might see a specific one like CF3CO2H, where you got the trifluoro one. This is kind of a common one. Or the other big one is MCPBA, right? The metachloro peroxybenzoic acid. So metachloro peroxybenzoic acid. And then, like I mentioned, right? So these are just all examples, right, of the generic peroxy acid. I will make a note, and I'll just put a little star next to this, a little asterisk here, right? You have to watch out for when you have alkenes and other things that are easily oxidizable, like sulfurs and sometimes nitrogens, like aromatic nitrogens. They can also get oxidized by the Baeyer Villiger. So watch out. Watch out for other reactive functional groups. Right, for us, a big one's going to be alkenes we want to worry about, because that's a real common reaction, is making epoxides from alkenes using peroxy acids. So what the Baeyer Villiger reaction does is it inserts an oxygen atom between the carbonyl and one of the groups that were attached, right? So let's say I have this ketone here, and I'm going to go ahead and I'm going to add my peroxybenzoic acid. So I'll use CF3 double bond OOH. Now, what I mean by insert is that you're literally just going to have your molecule the way it was, only now in between the carbonyl and one of the groups, there's going to be an O. And then the rest of the thing. So then I'll draw my other 2 carbons, right? So I had my original 2 carbons there. This was a diethyl ketone. So I have an ethyl still attached to the carbonyl, but now an ethyl attached to the O. So I inserted the O. Right, so this O right here is now this O right here. And you'll notice that in this example, I went from having a ketone to an ester. Right, also I went from having 2 CO bonds to having 3 CO bonds. So we've definitely done an oxidation. Sometimes these are called Baeyer Villiger oxidations. You might definitely see that. So Baeyer Villiger oxidation. We've oxidized up that carbon from a ketone to an ester. Now, in this example, I had a symmetrical ketone, so it didn't matter where I put the O, but in a more complicated molecule, it is going to matter because we have these preferences. So we need to talk about the migratory aptitude, or how likely groups are to move, right? Because like, let's say I have this ketone, right? Now the 2 sides are not the same thing. Because I could get one product, right, where I add the oxygen on the left-hand side, and I'll draw it like this, right? I could insert the oxygen over here, which is going to give me this group, but now there's an O there, and then attach the carbonyl and 1, 2, 3 carbons, so 1, 2, 3 carbons. Or I could have added it to the other side of the carbonyl, which would give me the isopropyl on the left-hand part of the carbonyl, but then the O, and then the 1, 2, 3 carbons. Right, so depending on which side you put the O, you get 2 different esters. And so we need to talk about the migratory aptitude. And again, the migratory aptitude basically is just talking about how likely is that group going to move. And you all kind of have talked about this before when we did carbocation rearrangements. Right, so migratory aptitude just talks about the rate at which a group moves. And again, we saw this with carbocation rearrangements also. carbocation rearrangements. And if you remember back to carbocation rearrangements, we said that the hydride shift was way faster than alkyl shifts, right? H's move faster than alkyl groups are. So our fastest, I'll put right here, fastest, is going to be hydrogens. They're going to move faster than anything else. And then after that, basically it's the most substituted down to the least substituted, generally speaking. It kind of follows cation stability rules. So you'd have a tertiary group would move faster than a secondary group, which moves a little bit faster, but on par with like a phenyl group, like an aromatic ring group. And then primary group, and then lastly, methyl groups move the slowest. And now there are other considerations, like there might be a really powerful steric reason why something might move out of this order. Or if something is really electron poor, it might move a little bit faster than something that's more electron rich. But generally speaking, you're not going to see crazy examples like that for this class, where this is just first level organic here, for first term organic here. First year organic, not first term. So we definitely want to know this. This is going to be crucial for us, right? So if I look at that ketone that I had up there, and I'm adding my CF3, CO3H. What I'm doing here, right, is I'm asking myself, okay, on the left-hand side, right, this group right here, this thing that's attached, let me erase that arrow. This group right here, I would say is a secondary group, right? Because if I broke that group off, right, so if I popped that group off, it would just look like this, right, where this is that green atom. If I pop that group off, that group would be a secondary group, right? I know it's tertiary when it's on the ketone, but as a group, separate from the rest of that thing, it's a secondary group. And so that would be a secondary group, which moves relatively quickly. It's kind of in the middle. And if I took a look at the group on the right-hand side, right, I'm going to cut that off right there, and I look at that, which would just be this piece, right, where again, this blue carbon right here is this blue carbon right here. That's a primary carbon. That's a primary group. And again, I know it looks secondary on the ketone, but we're talking about it as a group separate from the ketone. So I've got a secondary group and a primary group, and I know from my migratory aptitude that secondary groups move faster than primary groups, which means that the correct answer for this is where I moved the secondary group. So my correct answer should be where I have an O with that isopropyl group on there, and then my my carbonyl, and the rest of those 1, 2, 3 carbons. So this would be your major product. And again, it's just because one group is secondary, one group is primary. The secondary group moves a little bit faster. And so that's how we predict. That tends to give us the major product. So this will be really important, and I'll do a few more examples here in a little bit. Let's take a look at the mechanism. So same reaction here. I've got that same ketone. I've got the trifluoro peroxy acid here. And what I want to do is I'm going to go ahead and add some electrons. Maybe. There we go. Add some electrons. I'll draw my peroxybenzoic acid here. Or not benzoic acid, my peroxy acid. CF3. And what happens in this first step is you're just going to protonate. You're just going to protonate your carbonyl. Now, you might see reactions written out where an acid is added to this. You might see an extra acid added to help with this protonation step, or a Lewis acid like BF3 or something like that. But the idea is you're going to have some sort of protonation to make that carbonyl a little more reactive, more electrophilic. Right, so now you have a positive charge on that oxygen, which makes it a lot more electrophilic. And if I draw the conjugate here of my peroxy acid, now that oxygen is negative. And what we're going to see here, right now that this carbonyl has been activated, it's been protonated, so it's a lot more electrophilic. And maybe actually, let me draw the resonance structure here, just to emphasize what I'm talking about. If I look up at the first ketone, right, I would put my partial negative on the oxygen, partial positive on that carbon right there, right? If I protonate it and I look back at the thing that I just drew here with the hydrogen on it, this actually has a resonance structure where I can take those electrons and move them up. And I can draw now where there's a full charge on that carbon. All right, so I have this resonance structure here where now that positive charge actually moved onto the carbon. So it's a lot more electrophilic carbonyl carbon, right? We go from a partial positive in the top drawing, in the original structure, to now I have a resonance stabilized carbocation where it spends a lot of its time on that carbon. So the point is that carbonyl carbon is a lot more electrophilic. I don't care which of these resonance contributors you draw your next step going to. I feel like students kind of like to see the full positive charge on where the thing goes. So I'll draw my negative oxygen going to this partially positive carbon, which is going to give me another reversible step. So I've got that isopropyl group. I've got the oxygen with the hydrogen. I've got an oxygen and an oxygen attached to the CF3, and then there was this propyl piece attached. I think that's all of my stuff. And let me get those electrons, right? If you're drawing a resonance, or sorry, if you're drawing a mechanism, make sure you show all the electrons. So this is that kind of hairy, stable intermediate piece, right? Where the idea is that this peroxide bond is unstable. Right? Peroxide bonds are unstable. They want to break. They're gonna break. They're not gonna stick around forever. And so that's what we're gonna see in this step. It's not a very intuitive step, but it appears from a bunch of studies that were done, and there have been some great studies done with this. We're not gonna go over them right now, but it appears that what happens is that when these electrons can drop down, right, to form a carbonyl again, and then one of these groups attached to this carbon is going to pop off, right? Is it going to be the isopropyl group, or is it going to be the ethyl group, or sorry, the propyl group on the left? And we talked about how one of these groups migrates faster than the other one, and the one that moves or rearranges faster and more easily is the isopropyl group. So we're going to see this isopropyl group here, right? This carbon right here is actually going to get kicked out onto this O, which breaks the peroxide bond, which again we were saying is a really weak bond. It wants to get broken. It wants to take electrons from something. And so by making it move like that, we are able to have a lower energy system altogether. We've gotten rid of that unstable peroxide bond, that high energy peroxide bond. And I'm going to draw this once in a weird looking way, and then I'll kind of fix it up so it looks more like we want it. And so this would be a one direction thing, right? So my first step was reversible, second step reversible. This is a one-way thing because you're not going to reform a peroxide bond ever. So if I just keep the same shape, just so you guys can follow the pieces here, right? There's a double bond there now because I had those electrons drop down from a double bond. The isopropyl group, though, moved. I'm still attached to the O that was right here. But I said the isopropyl group moved to that O, right? The whole group moved over. It's like a methyl shift or a T-butyl shift, or when we do those carbocation rearrangements. And then I have now the carboxylic acid, CF3, this nice, stable, resonance stabilized carboxylic acid, the trifluoroacetic acid here. And you notice that my drawing down here looks kind of funky. I don't like the bond angles. It looks kind of ugly. But I'm going to leave it and I'll fix it up in a second. And as you can imagine, this last step, right, you have an O minus, you have a positive on a carbonyl that's not terribly stable. It wants to take electrons back. What's going to take that hydrogen? Probably the acetic acid is going to be the thing that takes the hydrogen. Whatever takes the hydrogen, I don't care. And then we've got our product, which again, I'm going to draw this out so it looks more like we would expect. I have the isopropyl attached to the oxygen. That oxygen's attached to the carbonyl. That carbonyl is on also attached to 3 more carbons. And so let me label this out even further so we can really see it. Right, if I call these over here on the far left column, if I call this carbon 1, 2, 3, 4, 5, and 6, this is now my carbon 1, 2, 3, 4, 5, and 6. And down here on that precursor step, 1, 2, 3, 4, 5, 6. Right? 1, 2, 3, 4, 5, 6. So I was able to keep all of my I was able to keep track of all of my carbons. I moved the group that is more likely to move, that has a higher migratory aptitude, onto the oxygen, the first oxygen in that peroxy acid that you're using, so that I can get my product, which is again going to be the ester in this case, or it's going to be a carboxylic acid if you have an aldehyde, but it'll be an ester if you have a ketone. And so you form that and your CF3CO2H. Right now it's just a regular carboxylic acid. That's the mechanism of the Baeyer Villiger. You should know this mechanism. Now for some examples, right? So again, I'm just going to look at these and ask myself, well, of the true groups on either side, which one is more likely to move, right? So for my first one, I have an aldehyde. This group is a primary group. Here we just have straight up hydrogen. I know that hydrogens move faster than anything else, so that means I need to insert the oxygen on that side, right? Which in this case gives me my aldehyde gets oxidized up to a carboxylic acid, not an ester like we saw with the ketone. If I look at the second one, same thing. I've got a primary group. I've got a secondary group that's an aryl group. It's an aromatic group. But either way, the secondary group is going to move faster than the primary group. And so I'm going to insert on that side also. So O, and then my aromatic ring. So this would be the ester that I'd make from that ketone. So again, I would pause for a second, see if you can do these last three. One of them has a little tricky thing you got to keep an eye out for. Actually, none of these have a tricky thing. We're good. I'll do a tricky thing in a second, but try to pause and take a look at the last three. So now let's look at this third one. In this case, I have a primary group versus a methyl group. So I'm definitely going to go to the primary group side. That's more likely to move than the methyl. So whoops, I lost a carbon. There's my third carbon. Definitely count your carbons with this. You just saw me lose one. It's very easy to lose carbons when you do these things. So I've got a propyl piece and a methyl piece. That looks perfect. Now, you might come up with problems like this, where this is a primary group and this is a primary group. So neither one is necessarily a lot more apt to move than the other one. And so you're probably going to get a mixture. So I would just draw a mixture, right? So I'm going to draw one. So 1, 2, 3, 4. 1, 2, 3, 4. I'm going to draw one where the oxygen adds on the left-hand side. And I'm going to draw one where the oxygen adds on the right-hand side, right? Because they're both primary. It doesn't matter that one is longer than the other one. That's not what's driving it. It's an electronic thing. It's how stable is that slight positive charge that happens in a transition state, because it's losing electrons a little bit. So they're both primary. Both of them move at roughly the same rate. So you'd expect to get a mixture of products here. And then lastly, you might see cool things. So here's again another one that's both primary, but it's symmetrical, so that's not really a big worry. What's kind of interesting about this one is that it's going to be a ring expansion, right? So now I have a 5-membered ring, but I'm going to have a 6-membered ring, right? Because if I decide to add it to the right-hand side, now I've made my ring slightly bigger, right? Because if I label these carbons, let's say I label this carbon 1, 2, 3, 4, and 5. This is carbon 1, 2, 3, 4, and 5. There's now a 6th member of that ring, namely that oxygen. So Baeyer Villiger reactions are pretty straightforward. The only thing you'd have to worry about, let me just do this off to the side here, again, is if you had a problem like this, say you had something like this and you added MCPBA, some peroxy acid. The idea is that you just want to be mindful of the fact that, yeah, you'll probably get some product like you want, right? So where I get some sort of, I have a hard time drawing 7-membered rings. Is that 7-membered? I think so. Where I've expanded the ring, but you're also going to get some reaction that you didn't want, because MCPBA, as you may remember, also reacts with alkenes to make epoxides. So just be mindful of that fact. We'll learn some other ways to get around things like that, but right now just be aware, just remember that the peroxy acids also react with alkenes to make epoxides. So keep your eyes out for that. So do some more examples, do some worksheets, got practice problems in the book. Happy studying. Good luck. Please let me know if you have any questions.